Hello everyone, welcome back. So, we are talking about total variation. So, basically we looked at the schemes, several schemes for convection, and we found that schemes which have less dissipation, uh, mostly for example, the schemes like McCormack and all. Okay, so or even the Lex Vendroff or even leapfrog schemes. So, we found that they have got lot of wiggles with what we call as the Gibbs phenomena near the discontinuities, right. And one measure of that discontinuity or the basically the wiggles that we are that are forming is basically the total variation. So, that is what we are talking in the last class, and we said that okay, it can be taken as the let us say you have some grid points, this is j plus 1, j minus 1, okay, I j does not matter, and this is let us say it is 1D, and you take the value at every single point, I mean every uh, stencil, basically j minus 1, j plus 1 minus j plus 2 minus j plus 1, and so all of them, and basically take the summation of that, take the absolute value of that and take the summation of that. So, that gives you the total variation. If you look at the continuous form of this is basically nothing but delta x del u by del x at j, right. So, this is because if you take this u j plus 1 minus u j, okay, let us say by delta x, and you multiply by delta x, and you say that delta x goes to 0, then it will become basically du by dx. So, it is basically measure of the how we are approximating this gradient using this numerical method. Okay. So, what we are trying to see is that let us say if you have a step function like this, or a function which is like this, which we have discussed earlier, there are two steps here, here and here. Okay. So, here the total variation, the value is, if you do u j minus u j minus 1 all across here, that will be 0. Here it will be, it is going from 0 to 1. So, the value is equal to 1, the total variation is equal to 1. Here again it is 0, okay. Here it is again equal to 1, and it is again equal to 0, right. The total variation of this entire thing is equal to T b equal to 2 in the beginning, right. Now, as you apply the numerical scheme, if the wiggles start forming, let us say you have this large wiggles which start forming, then what will happen, that the total variation will increase, right, because now you have lot of variations here and they will contribute to this. So, now the total variation will increase, and which is not good for a numerical solution. So, that will lead to the Gibbs phenomena. So, we want to avoid that. So, we are looking for schemes which are basically total variation diminishing. Okay, that means the total variation at the next point, next time stamp should be less than or equal to total variation in the current stamp. Okay. So, that is what is happening at n plus 1, the total variation during that time of the signal should be less than or equal to total variation at the current time, which is n. And then such schemes come under the category of monotonicity preserving schemes, which we discussed last time. Okay. So, now let us see that what happens when you are using trying to calculate the total variation. So, this is the initial square wave that we have, okay, and we are using FTBS, okay, Lex-Frederick, Lex-Pendorf and the McCormack. Okay, all of them have value around this is little bit ahead of 0. So, around 2, okay, all of them, as I mentioned, this is the total variation is 1 here and 1 here, okay, and this is 0 here, 0 here. So, if you add all of this, then it becomes 2. Now, what happens with time? So, let us see this movie. Okay. So, if you play this movie, this is the one where I am trying to get this total variation for FTBS, Lex-Frederick, Lex-Pendorf and McCormack. In this in the McCormack, I have not used any smoothing here. Okay. So, once you run that, so you see this is with time, the solutions are getting developed. Okay. So, let me stop it here somewhere. Okay. So, you can see that the McCormack value is around 9.9, Lex-Pendorf is 10.58, Lex-Frederick, which I told here is 4.81. Okay. The value goes to very high. So, if you go to the, let us say near the last time step, around 10. So, it starts from total variation of 2, which is due to discontinuities on the at the steps. It has gone to value of 10, which is not a good thing for a numerical scheme. McCormack had lot of variations here, lot of wiggles here, more than Lax Van Dorf if you see for the nonlinear convection. Okay, so what I was showing you, which when we apply the total diminishing. So, what we do here is, so this is the property that we have seen, that FTBS, it is TVD. FTBS, if you recall the movie, it is the value is not increasing, however, it is highly diffusive. Okay, then Lex Frederick, it is more diffusing than FTBS, and it is showing it is also basically TVD decreasing because it is variation diminishing. So, what we are seeing little bit increase in the TVD was because of the wiggles which are forming while it is going like this, okay, going up in the first step, but then if you increase or make this grids smoother, then it will go away. Then all these Lax Van Dorf and McCormack, they are not TVD. Okay. So, you basically what you need to do is that you need to use some smoothing function here, so that it becomes TVD, that is total variation diminishing. And how do you do that? So, I will just show you for the McCormack. Okay. So, you take the whatever value that you are coming from the McCormack and then you add some dissipation here. So, what it does that let us say this is where your wiggles are forming. If you smoothen this out, so you basically add the dissipation everywhere, then it will start going like this, it will start dissipating like this. Okay. So, the variation will not increase. This is one way. There are several ways to diminish the total variation, and this is one of the ways, and we will look at some other ways, some more ways when we go to the solve the actual problem. And this is the diffusion, it can be like you can choose any diffusion coefficient, the kappa value, I have chosen for example 0.02, and then this is the typical value when you are, let us say you have delta u by del x square, right. So, this is how you look like by delta x square, which is observed in the code earlier. Okay. And then if you add this dissipation, and that is what will happen, which we saw in the movie earlier. Okay. Now, this was the McCormack with the dissipation, okay, which we saw earlier. Okay. Now, if you use an adaptive sensor, so the sensor that we talked about earlier, I mean there was no sensor there, what we said that we are adding dissipation everywhere, right. So, when you add the dissipation everywhere, it will not only basically smoothen out in this part, but it will smooth out everywhere, right. So, the shock that you want to predict, the strength of the shock or the location of the shock, both will have lot of diffusion or the dissipation because of the sensor that you are using. So, what is typically preferred in the literature, or when you try to add smoothing on in these schemes, you just look for where the shock is, right. So, you can use some kind of basically gradient of the pressure. So, this is one scheme that I am talking about, this is called switch. So, what does it do, that it will only activate when there is a shock. Why? Because you know that across the shock pressure increases. So, normally in the regions where there is no shock, the value of this will not be very high. So, this is basically Pj minus 1 minus 2 Pj plus Pj minus 1. So, you are in, let us say in cell J, and you are trying to calculate the viscosity that you want to apply there. So, it will only be activated when there is a shock. If there is no shock, then the value of on top and bottom will be very small, right. So, this will not be activated, and k nu or kappa nu is the value that you can choose, you can take it to be maybe 0.05 or 0.02. So, how is it different from the diffusion that we applied earlier? So, earlier we had uniformly applied everywhere, right. So, we just added this dissipation term, whatever value got from McCormack, we added this dissipation term, and it smoothened out everywhere, not only in this region, but everywhere, right. Now, once you apply this sensor, it will only smooth out solution very close to the location where the Gibbs phenomenon is happening. Okay. So, wherever there is a shock. So, then you can, this is the diffusion term which will be applied to the McCormack solution, but nu j is if you look at, this depends on index j, right. So, at some j's where there is no shock, this will be 0, and where there is a shock it will get activated, and the beauty of this solution is that it will not smoothen out everywhere, and it will try to preserve the solution away from the shock as it is, and all it will only smoothen out the solution near the shock, right. So, this is one of the implementation using the Python code. I will probably share these codes with you, so that you can take a look. The movie file is not working here in this format. So, basically this is the final solution that we will have. Okay, so, here there is a pure McCormack, okay, there is a blue one here. Okay. Then when you have constant smoothing, so you can see when you do constant smoothing, it changes the behavior here also. The red one is the constant smoothing. Constant means I have just used this dj term everywhere, the diffusion term everywhere, okay, without caring whether it is near the shock uh, or near the expansion or any other region, right. When you use adaptive sensor, that means that you look for the location where there is a shock, and then you apply the smoothing at that location. So, then you can see that the green and the blue curve are almost top of one another away from the shock. Okay, only when you have the shock which is happening here, say it has decreased, the blue one is the without any sensor or without any diffusion, and green one with adaptive diffusion. And you can see that the amount of amplitude has decreased substantially. If you increase the value of kappa nu, it will further go down, and it is again an art that how much diffusion you want to add to just predict the shock without any wiggles, but also do not smoothen out solution too much, do not smear out the shock. And you can see that the predictions are very close to the analytical solution that we get from the equation. Okay. So, I just wanted to briefly tell you how you can add some dissipation or the diffusion term in the numerical scheme if the schemes are behaving very weirdly near the discontinuity, right. So, as I told you that there are several approaches. Okay, you can apply some kind of filter, okay, or you can, I mean, there are several ways to do about it. We will talk about these later. So, now we have all the recipes. So, we know that we have looked at several schemes, okay, and we are able to solve the problem of sufficient complexity. But what we have done so far is we have only looked at 1D problem, and it is a scalar problem. That means, the problem was like del u by del t plus c del u by del x equal to 0, or maybe the Burger's equation, okay, where it is non-linear, inviscid burger, viscous burger. What we have to go from here to solve the realistic problem in fluid dynamics is basically this u will become a vector now. So, now you will have basically rho u, rho v, rho w and rho e. Okay. The form remains the same. You will have basically a non-linear term, a diffusion term which is coming because of the viscosity or the Reynolds number, okay, and then you will also have something called pressure gradient term, right. So, before we go to the more complex problem, there is one thing which is just missing in all these problems, is that we are somehow able to smoothen out these shocks here, but we want to see physically that what are the approaches in the literature which basically handles this kind of phenomena. Okay. This kind of phenomena are called the Riemann phenomena. Okay. So, we will just look into that problem, the Riemann problem. This is after the mathematical Bernard Riemann. So, that is the thing that we will discuss, and then we will go and solve the realistic problem using Euler equations. Okay. So, let us go to the Riemann problem. So, to motivate you for the Riemann problem, I look into a gas dynamics problem which is called the Sword shock tube problem, or just the shock tube problem. Sword was the scientist who gave the condition of the pressure and the velocity, but it is basically shock tube problem. So, what happens here is basically this is a shock tube what you see here, okay, and there is a diaphragm at the center, okay, and on the left side you have very high pressure and the right side you have low pressure, okay, and they are separated by a diaphragm. Okay. This is at t equal to 0. Okay. What will happen as you increase the pressure on the left hand side, okay, keep on increasing, okay, at t just 0 plus, okay, the diaphragm breaks, and because of the high pressure the waves start traveling on the right hand side, and the solution to this is you will have a shock which is traveling on the right, expansion fan which is traveling on the left, and in between you will have a contact discontinuities. It is called contact discontinuities because basically your density is discontinuous here, but the pressure and velocity both are continuous across the contact discontinuity, right. If you recall, we talked about Euler equations, and in the Euler equation we had 3 waves. Okay, there was entropy wave and then 2 acoustic waves. So, this is due to the entropy wave. The entropy is basically discontinuous across the continuous contact discontinuity, right. And this is just shown basically in another form, in xt form. This is x and t, right. So, this is a characteristic line which is coming due to the shock. Okay, then there is one due to the contact discontinuity, and there is an expansion fan, okay, with time. So, if you can go any time and you can see that there is a shock location here, the contact discontinuity here, and this is the expansion fan, this is the expansion fan, right. So, we want to solve this problem. So, yeah, what Sort did, that he gave the condition, okay, for example, rho equal to 1, p equal to 1 on the left hand side, and you can see that on right hand side p equal to 0.1. So, basically if you take the ratio of P r by P L, that is 100. So, this is basically 10, this this is P L by P r, right. So, the left side of pressure is basically 10 times the pressure on the right hand side, and similarly if you have the density, okay, which is basically 8 times the density on the right hand side, right. This is 1 to 5 and this is 1, right, and the velocity is 0 on both the sides, and you can solve this problem analytically for an Euler equation, okay, and you can basically find out the position of the normal shock and discontinuity and the expansion fan at any given point of time. Now, we want to solve it numerically. So, how will you solve it numerically? Okay. So, this is the condition once again. So, you have to solve the Euler equation in 1D. This is in 1D phenomena. This is just a separation by a diaphragm. Left side is your rho L, P L and U L, and rho R, U R and P R. Okay. And this is the Euler equation that we have discussed. This is in 1D. We do not have to basically take the viscous part in the beginning, okay, for the solution, and this is for the energy, the total energy, internal energy plus kinetic energy, and this is the rho e. Okay. So, we have discussed this in the Gaussian equations, correct. So, this is the vector equation that I was saying, that now that you have the recipe of del u by del t plus c del u by del x equal to 0, you all you need to do is that define u as a vector of rho u and rho e and try solving it. Okay. But then it is not as simple, and the reason for that is basically the discontinuities. If you look at let us say this is x equal to 0, okay. If you look at the discontinuity as the shock forms, the shock will have a discontinuity like this, right. If you plot this across the shock, this is my shock, okay, and this is your U L and this is U R, right. So, this is what is called the Riemann problem. Okay. You can do it for basically even linear convection also. I am showing it for the realistic problem, which is the short shock tube. So, basically what we are trying to see, that we want to solve this problem numerically, but then what happens, then that a shock gets formed. Okay. Now, how do you basically calculate the values across the shock, left and right? Okay. So, this problem is called the Riemann problem. If you want to define it formally, okay. So, let us do it for a linear convection equation. So, we have this expression del u by del t plus c del u by del x equal to 0, right. So, the Riemann problem will be for x, let us say this divide it, this is x, this is x equal to 0. So, you have something on the left which we call as u L, and something on the right which can be 0 also, I mean this is your u r. Okay. So, this is x greater than 0, you have certain value, x less than 0 you have certain value, and at x equal to 0 there is a discontinuity. Okay. So, there was a lot of discussion about how to solve this problem, and historically if you see, initially when people are trying to solve this problem numerically, they were getting the Sock equation long. Okay. So, the location was not coming out to be right. For example, if you want to solve like this, you might get the Sock here, it is made out but still here, or maybe Sock coming out here, but not at the correct location. Okay. And actually this troubled the CFD users for a very long time, that how to solve this problem numerically, right. This is until Godunov came and he proposed the approximate Riemann solver. So, if you solve it analytically, there is a way to exactly solve this problem. Okay, that is very expensive. We will not discuss that in detail here, but when you try to solve it numerically, this was the issue which is happening, that sometimes it was coming on the left or the right, it was not coming at the right location. So, this problem was posed by Bernard Riemann. This is also called the Dambruch problem. If you work in hydraulics, so you know this, let us say there is a dam here, okay, there is a lot of water here, and there is a the water level is lower here, and at t equal to 0 plus the dam breaks, the water will flow here. Okay, so, this is also called the dam break problem, and there you use the shallow water equation, here we are using the Euler's equation. Okay, but I am first telling you for the linear convection equation, which is ut plus ux equal to 0. Right. For this we know the solution, that we have discussed earlier, that if you, this is a hyperbolic problem and the characteristic is dx by dt equal to c, right. So, you can basically plot this characteristic, okay, across the discontinuity is going like this, this is t and x, okay, and slope is 1 by c here. Okay. So, if you know the initial solution, you can get the solution any time, because this is just the solution marching by C t, right. So, if you know the any solution at x 0, you can take x minus C t at 0, and that will be the solution at any given time. So, u at x t is basically u l if x minus C t less than 0, or u r if x minus C t is greater than 0, right. So, let us take an example. So, let us say this is my Riemann problem, this is the initial condition, this is at t equal to 0, this will be my characteristic, and across the characteristics the left will be, so the C is positive here, okay, it is going on the right hand side, the convection on the right hand side. Okay, so, it will just get convected. So, whatever time, let us say this is your discontinuity and this is your C t. So, whatever profile you have, just put that profile and just convect it by that distance, right, the C t distance. So, this is what is the Riemann problem. You can take it anywhere, at any given time, let us say here. So, the Sock will be here, okay, go here, the Sock will be here, but the profile will not change. Okay. That is what we have learnt from the linear convection equation. So, you can actually, what will come to this later, we can represent for a more complex problem this entire thing that we are writing here, UL equal to, if UL and UR depending on whether x minus it is less than 0, greater than 0, in terms of basically UL minus UR, which we call as the wave strength, and the C, which is basically your wave speed. Okay. So, when you try to solve this numerically, and how we have solved till now, you might say that we have already done that, but what is happening, if you recall the MPD part, the modified PD, although we are solving the equation ut plus cux equal to 0, and when we are using, let us say FTBS, we are not solving this problem, we are rather solving this problem of ut plus cux is equal to nu uxx, right, this is just the numerical viscosity that we talked about, right. This is the MPD, and of course, this nu depended on the delta t, delta x, and so on and so forth, right. So, this is we are able to solve this problem because we use something called the vanishing viscosity model, okay, which is basically, instead of solving the problem ut plus cux equal to 0, we cannot solve it numerically for this condition. The reason for that is both ut and ux are undefined, okay, at discontinuity at x equal to 0. You cannot get this del u by del x, because you know the solution at left, solution at right, and they differ by a large magnitude, and the at x equal to 0, you cannot basically get the gradient, because it is not a smooth function, right. It is a discontinuity here. Similarly, del u by del t also is not defined, right. So, Riemann solution is not a classical solution, right. So, how are you able to solve it? One is the vanishing viscosity model. So, for any value nu greater than 0, it will work. Okay. So, what will happen, that instead of getting this solution which is the black line, you will get the smoothened out solution which is the red line. So, instead of getting like this, you will get something like this. Okay. So, we have basically smoothened out. The other approach is basically what is called the integral form or the weak solution, and we had a brief discussion about it earlier. So, what we do is that we will integrate that equation over the control volume, which is so we will consider a control volume basically let us say x1 and x2, and the time. So, this is my x and this is my time, okay, and between let us say time t1 and t2. Okay. So, you have a control volume like this, okay, and this is my actual expression. Okay. You see that I have written this C inside. So, I will come to this point. So, I will call it as flux. Okay. So, instead of writing del u by del t plus C del u by del x equal to 0, for problems of interest we will have this del u by del t plus del f by del x equal to 0, which is nothing but a conservation form, and this is very important. Okay. Here it is linear, so that does not matter, but in the non-linear problem it is very important to put in the conservation form. So, that is why I put in bracket, as I told you, it does not matter in this particular case, because C is constant here, but when you go to the non-linear case you will have those issues that you cannot use this form. Okay. So, once you integrate it over a distance and over a time, okay, and then use the regular theorems in calculus. Okay. So, you basically put the value in. So, when you are integrating in x, so you put this value of t2 and t1 and integrate in x. Okay. So, basically what is happening is del u by del t plus c del u by del x, basically dx dt equal to 0, and then you are integrating it. Okay. So, this is for dx. So, you basically when you integrate it, so with respect to dt, so that will become, you take this part integrate with dt. So, this you can be du by dt dt, this is t1 to t2 and then x1 to x2, this is dx, okay, for the first part. And for the second part, what we will do is that we will do this t outside t1 to t2 and this is x1 to x2 du by dx dx and then finally dt 0. So, once you work that out, you will get this expression. Okay. So, what we are getting is that instead of writing the problem which is this one, where the del u by del t and del u by del x is not defined, you write the problem in this form. Okay. So, here there is no differential with respect to t or with respect to x, right. So, this is a weak solution, this is the integral form of the same problem and this is called the weak solution, and this can be solved. Okay. So, this is what we do in finite volume. Okay. So, we will have shortly the discussion about the finite volume in the next class. So, what we will do is we will look at the Riemann problem and we will see how we can solve using weak solution. So, till now we have basically used the model which is similar to the vanishing viscosity solution, where we use a scheme which is dissipative, dissipates the value near the shock, okay, and that is how we are able to solve the problem. So, instead of solving a problem which is del u by del t plus c del u by del x equal to 0, we are solving del u by del t plus c del u by del x equal to nu del u by del x square, right. But what we can do is basically we can solve it in weak form, and which is actually a better approach to approximate the shock numerically, and we will look at this weak solution in the finite volume framework in the next class. Thank you very much.